This is not the easiest problem to find the electric field, but it's always one that gets started with. Maybe it's easier to set up, but so here's the problem. We're going to work through this. We're going to do every single step except for looking up something in an integral table, and I'm also going to do a numerical calculation. So if this takes an hour, this takes an hour. I'm sticking here until this is done. Okay. I might even make some mistakes because that might be fun. Here's the problem. I have a charged rod, a stick. It has a length L and a total charge Q. And I want to find the electric field over here. So how do we do that? Well, let's just do it. Let's start off with a reminder. If I have a point charge over here, I'll call that R1, and I want to find the electric field over here at RO, the observation location, I can find the vector R. And then the electric field, where R is RO minus R, then the electric field due to that one single charge would be E is 1 over E1, I'll call it 1 over 4 pi epsilon naught Q1 over the magnitude of R squared R hat. So I had to find the unit vector and the magnitude of that vector. Now, the unit vector R hat is R over R magnitude. I'm doing this on the side because it's not really the big deal, right? This is the big deal. And if I put that in over here, then I can actually write this as E1 as 1 over 4 pi epsilon naught Q1 R over the magnitude of R cubed. This and this are the same thing. Okay, we're going to use that. So here I have an infinite number of charges. So when you have an infinite number of charges, one thing I can do is to break it into pieces. I can break this into pieces and, imagine that I have a piece size right there, and there's my charge. I'll call this dq, right? Because it's not the whole charge, it's just part of the charge. So what I can do is break this into pieces and pretend like each one of those pieces is a point charge. So I have an infinite number of infinitely small point charges, but they add up to the total charge Q. Now let's give this charge a location, and let's give this observation location. So I'm going to call this vector R1, just for now. R1, and this is the origin, and this is the vector RO. So let's write these as vectors. I can write R1 as the vector 0, y, 0. So this could be anywhere along here, right? But it's going to have some y value, and it's on the y-axis. So its x value is 0, its z value is 0. It only changes in the y direction, the way I've set up this rod. Of course, you could put it in another direction, but this is just easier. And the same thing, RO is some location. I'm going to call that, so this is y, and this will be x, because if that's the origin, this will be x, 0, 0. So I can change the value of y, I can change the value of x, and I can do that. And with that, I get r as RO minus R1. That's pretty easy to do. So that's going to be the vector x minus 0, 0 minus y, 0 minus 0. There's my vector r. And remember, I'm trying to put it in this equation right here. So I'm going to need the magnitude of that vector so I can cube it, right? So let's find the magnitude of r. The magnitude of r is pretty simple. It's just going to be the square root of x squared plus negative y squared, which is y squared plus 0. So there's my magnitude of r. And we could draw that right here, right? That's my r value right there. And then this is going to be my electric field. It's going to be pointing away like that. That's E. I'm going to call that DE. So let's write down my expression for DE. It's not E, right? It's DE because it's only due to this single charge DQ. DE vector is 1 over 4 pi epsilon naught. That's a constant. DQ, I couldn't remember if you used capital or lowercase q. And then I need to divide by the magnitude of r cubed, and r is the square root here. So I'm going to write this as x squared plus y squared to the 3/2, right? Because this is to the 1/2 power, and then I cube it, so I get the 3rd power. And then I have to multiply it by the vector r, which is x negative y 0. So that's kind of an important thing, and I put boxes around important things. That's why presents come in boxes, because they're important. And that's my box. It's a present. It's a physics present. Now, this is just the electric field due to that one generic piece right there. I want to add up all the pieces. But I think now is a time to kind of invoke a trick, right? If we can use some type of symmetry in this situation, it's going to make our life much easier. And so the symmetry here is, I'm going to use this in purple. Imagine that I'm going to add up all the electric fields into all these pieces, right? Because if I have more than one charge, the net electric field is just the vector sum. So I need to add up all these electric fields into all these pieces. Well, there's going to be another piece down here that's negative y, and it's going to have an electric field pushing that way, not pushing, pointing. And it's going to look just like this, except that this value, this is the same. This is going to be plus y, right? Because this is in the plus y direction. So I'm going to have these two pieces add together. One of them is going to have negative y, one's going to have positive y. And when I do that, the y's are going to cancel. And you can see that up here too. The y component of this, the y component of that are equal and opposite, so they cancel. So this means that I only need to worry about the x component of the electric field. So let me rewrite this as a dEx. dEx, a scalar value, now I don't have to worry about vectors, is 1 over 4 pi epsilon naught dq over x squared plus y squared to the 3/2. And then I have the x component up here, so I have x. That's my x component of the electric field due to all these pieces. Now I just need to add all those up. Now, let's just think for a second. And I'm going to get out my purple. I'll use red. I got it red right here. As I add up all these pieces, I'm trying to find the electric field at this location x. So in this expression, x is not a variable, right? It's a parameter. I'm going to give it a value of x. I'm not going to change that as I move all these. What I am going to change is y. So that value changes, y. So I'm going to integrate this over y, not x, over y. But dq, each piece they're going to have the same charge, but it's a different location, right? So I have a problem here. And the problem is that I'm changing this along the y, but my integration variable is dq, right? I could integrate both sides of this equation. If I integrate, I'm adding up in infinite pieces. That's what that is. For both sides, well, that's fine. The integral of dEx is ex. So that's going to give me the total electric field. But over here, I need the limits of integration, and I don't have my variable y and my integration variable are not the same. So we need to fix that. So let me rewrite this equation right here, because that's where we're at. And I'm just going to say dEx is 1 over 4 pi epsilon naught x dq over x squared plus y squared to the 3/2. That's where we're at. And if I draw my rod again right here, I can use a trick, right? So this is my dq piece where the total charge is q and the length is L. So if I have uniform charge, then this piece has some width. And its width is going to be proportional to the amount of charge. So I can write the following. I can say the charge on this piece divided by the length of its piece, which is dy, right? It's in the y direction. So I can say dq over dy is equal to the total charge divided by the total length, q over L. I mean, that just says it's uniform charge density. This is technically the linear charge density. It's the charge per length, same thing. Now I can solve this for dq. I get dq equals q over L dy. Now I can put this in up here and look what I get. I have my integration variable dy, and I'll get rid of the dq. So dEx is 1 over 4 pi epsilon naught x q over L dy over x squared plus y squared to the 3/2. Now I can integrate both sides. Now, this is I don't need to put limits on both sides, because if I did that, you don't need to do that. So this is going to give me just EX, and I'm going to integrate from negative L over 2 to L over 2, right? Because if this is in the middle, down here is negative L over 2, up here is positive L over 2. So I just need to integrate this. Let's just rewrite this just to make it a little bit simpler, because some of the stuff is constant. Anything that's constant I can pull out front. And I get 1 over 4 pi epsilon naught. X is a constant. It does not change in this integral. It is a constant, so I can pull it out front. X q over L, integral from negative L over 2 to L over 2 dy over x squared plus y squared to the 3/2. And I can't pull that x out because it's in the square root thing. So it's in the integral. But then this is an integral that only changes with y. So how do you do that? How do you integrate this? Now, if you're great at integration, I actually don't remember how to do this. The first thing I would think of is to call this u. U is x squared plus y squared. But if you do that and I take the derivative, I'm going to get a 2y dy, and I do not have a y up here, so that's kind of a bummer. That's my go-to integration method, right? U substitution. It's probably a trig substitution, but I don't really know. So what I'm going to do, you can use an online integral calculator to help you with this, but I want to show you the cool way to do it. So this, I remember getting this in as an undergraduate. This is the 28th edition of the CRC Math Tables book, and it has a whole bunch of stuff in there, but one thing it has is a list of integrals. So there's a bunch of integrals that you can look up, and I've already looked through all of these integrals. And what you want to do really is, you see up here, you can't see that. Integrals containing the form square root of x squared plus or minus a squared. And so we're integrating over x, not y, in the table. So our x's are our y's, and that's a constant. So we have a square root of x squared plus y squared raised to the third power. So if you flip through this, you can see right here, this one is the integral of dx over the square root of x squared plus a squared cubed, which is x squared plus a squared to the 3/2. That's what we have, right? Except we have dx is dy, and we get this. So I'm going to just copy that down. I'm going to change my y's to my x's to y's and my a's to x's, right? Because that's the translation that we have to do. So I have right here, just from the book, I have dy over the square root of y squared plus x squared cubed is equal to, and we're doing the plus, right? It's plus or minus, we're doing the plus. And in the book, one of the things in the book, it has a plus. If I use the plus on the top and it's plus on the top, then it's still plus. If it's minus over plus, it just means you switch the sign. So I get that's equal to y. Sorry, I forgot. A squared is x squared times the square root of y squared plus x squared. That's my integral table. So I can put that in up here, not a problem, because now this is the exact form up there. I can put that in, and I get EX is 1 over 4 pi epsilon naught x q over L. That's all that constant stuff that didn't change. This integral becomes this, which is, I'm going to put a parentheses around here, y over x squared square root of y squared plus x squared. And we're not done because we have to evaluate it at negative L over 2 to L over 2. Okay. Are you having fun? Because I'm kind of having fun. I don't know about you. If you made it this far and you're having fun, I'm having fun. So let's have fun together. Let's see. So this, I can pull this out. That's a constant. It's going to cancel with one of those. So let's just cancel that. That's fine. Now I just need to put in L over 2 and then minus L over 2. I think let's just do this on another piece. We don't need to squeeze it in here, right? We have plenty of paper. Okay, so I'm just going to do it like this. EX equals 1 over 4 pi epsilon naught Q over L Q over XL. I pulled that X out. And then I'm going to put in my L over 2 for Y, and then minus L over 2 for Y. So if I put in L over 2, I get L over 2 over the square root of L. Let's just put L over 2 squared plus X squared. And then I'm going to have to say minus this, which is minus L over 2 over the square root of minus L over 2 squared, which is just L over 2 quantity squared, plus X squared. And because I'm squaring this, so these things don't cancel. And then this is actually, I can just change that to plus, and so I get 2 of them. So if I add these 2 together, they have a common denominator, which is kind of nice. So I can add them together, and I get 1 over 4 pi epsilon naught Q over XL. And then I have 2 of those, so it's just going to be L over, I feel like I made a mistake. I can feel it sometimes. You just feel, no, there's the XL. Okay, that's fine. XL. It's a lot of algebra. If you make a mistake, that's fine. L over 2 squared plus X squared. And that L cancels with that L. And that's that. I'm checking over here. I wrote down the answer on the side. I think that's right. Okay. So now one other thing that we want to do, there's 2 other things. We want to do this more generically. So it's commonly done and in the book is to call this the vector, the scalar value R, right? So then if I replace my X values with R, then I can do that, and that's not too bad. I'm gonna do that in a second. Let me do that. I'm gonna do that. EX is 1 over 4 pi epsilon naught Q over R times the square root of R squared plus L over 2 squared. I switched the order just because that's the way I had it written up there. Okay, check number 1, units. Let's check if this has the right units. Oh, I moved my paper down. Does this have the right units? We know that the electric field due to point charge has units of 1 over 4 pi epsilon naught Q over R squared. So it should have the epsilon naught, got that. It should have a charge on the top, got that. And it should have distance squared on the bottom. So this here I have the square root of distance squared, which is distance, and then I have another distance. So the units, check. Okay, let's check what if L goes to 0. L goes to 0. So the length of this goes to 0, then this should look like the electric field due to a point charge. So if I put in 0 right there, I get R. The square root of R squared is R, and I get KQ over R squared. That's the point charge. Check. And now let's check as R goes to 0. As I get really, really far away, the electric field should go to 0. And you can see since R is on the bottom, as I do that, that's good. Okay. Now let's do one more thing. What if R is much less than L? If R is much less than L, then there is an approximate form for here. And I can't remember what I'm doing. So if that's true, L squared, if I just... Yeah. So this term right here is just going to be equal to, if that's true, then this term in here, inside, then it's just L squared over 2, square rooted, which is L over 2. And then I get EX is approximately equal to 1 over 4 pi epsilon naught. Then I have Q over R, and then I have L over 2. And then so we can write that as 1 over 4 pi epsilon naught 2 Q over L. That's the way they normally write it, over R. And so they write it as Q over L because that's the charge density. That's why you can write it. So there you go. It has the same units. Okay, we are halfway done. We did most of the work. But I want to set it up numerically. So in a numerical solution, we're going to do something a little bit different. We're going to do something very similar too, right? So here I have my rod, and it has a charge Q and a length L. I'm going to break this into finite pieces. I'm not going to let the piece size go to infinitely small, which would make it an integral. And instead, what I'm going to do is to break this into pieces, n pieces. This would be 6. Is that 1, 2, 3, 4, 5, 6, 7? I've broken. Okay, that one's not there. 6 pieces, and I'll do the same thing just for fun. I need to then find the location of each piece. I need to find delta Q, the charge of each piece, which is going to be Q over N, right? They're going to be 1/6 the charge. And then I can find the electric field at that point. So I'm going to go through here, do my same rules for finding the electric field, find the electric field, find the electric field, and then just add all those up. And I'm going to do that in Python. Now, to do that, I do need some numbers, right? Because I'm going to do these, add these up as numbers. So let's just pick L equals 0.1 meters, Q equals, let's say, 5 nanocoulombs. I'm just making up stuff there. It doesn't really matter. And then I need to pick the location here, but let's say that is 0.01 meters, so 1 centimeter away. Let's do that. That's my observation location. Let's jump over to Python and let's make this happen. We're going to make it happen. Okay, making it happen. Computer. Okay, I'm in Web v Python. I haven't done anything yet. We're going to do it all together. Let's just get started. And, you know, don't worry about making like perfect functions or anything like that. You can just do it. You don't have to make things perfect. And we're not going to make things perfect. Okay, let's go ahead and put K is 9 times 10 to the 9th. That's my 1/4 pipes. I'm not. Let's make that a little bit bigger. Let's make Q equals, what did I say? 5 nanocoulombs, so 5e negative 9. L equals 0.1. And I'm going to call this X. X is 0.01, just for fun. And then N equals 6. Okay, I'm going to actually draw the spheres just because it makes it more useful. And one of the ways we can do this is to like start at the lowest point at the negative L/2 and then move up a piece each time. And we're not going to do this the perfect way. Okay, it's not going to be perfect, but it's going to be fine. So what I want to do is to find that step size, right? How big of a step do I need? Well, if my total length is L and I have n pieces, then dy is going to be equal to L over n. So that's my step size. Now I'm going to put my starting location. I'm going to call this RQ. It's going to be the vector negative L over, no, 0, negative L/2, 0. So I have a location. I'm going to put a sphere there, and then I'm going to move up a location dy, 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 and make more spheres. So let's do it like this. While RQ dot y, that's the y component of RQ, is less than L/2, then make a sphere. So I'm going to make a sphere, and we don't even have to worry about putting it in a list or anything like that. We could do that, and we could make it awesome, but we don't need to. So I'm going to draw a sphere, and I'm going to give it a name. Sphere position equals RQ, and the radius is going to be equal to L over, let's say, L/20. I'm just picking up a value. Now I'm going to move the location of my charge. So RQ equals RQ plus vector 0 dy 0. So I'm going to move it up a position dy. And that's it, right? If I keep on doing that, I should make a bunch of spheres, because I'm going to eventually get to L/2 and it should stop. Let's run this and see if that does indeed work. There you go. 1, 2, 3, 4, 5, 6, 7. So I have 7 spheres, so that's not right. Okay. So one of the things I can do to fix this is, because I have 6, is to say as long as this is less than or equal to 1, 2, 3, 4, 5, 6. So then I stop. I'm exactly at L/2 and I stop. The other one added an extra one, but I have my 6 things. Now you'll notice that they're not perfectly positioned, right? Because this is at negative L/2 and that's at L/2, but they don't have to be, depending on the way I make them. And so you know they could be offset. They're not really in the center of those pieces, and that's fine. What if I want to change that to 50 spheres? Well, n equals 50. There you go, 50 spheres. See, so you see the power of this, right? I'm making all those spheres, and it's great. Let's make another sphere appear beforehand, and I'm going to call that OBS. It's a sphere. The position is equal to vector 0, x 0, and the radius is equal to, let's do also L over 20, just for fun. And let's make it yellow. Color equals color dot yellow. So that's where we're going to calculate the electric field. And it didn't show up. Oh, it's too close. That's why. Let's move x further away. So let's make that 0.6. Oh, in the x. Oh, I put it in the x direction. That's why. So 0, x 0, 0. That's right. There it is, right there. That's where I'm going to put it. So there's the location where I want to calculate the electric field. That looks a little too big. I'm going to make it a little bit smaller. Let's make all these things smaller. Make that half as big. Let's make these half as big too. Which doesn't really matter. I'm just making it look nice. Okay, there you go. So now I have all those spheres. I can go through and just do my normal method for calculating the electric field. So I'm going to say, find the location of this, the location of that, find the vector r, and then find the electric field. And then I'm going to add it to the total electric field. If I want to add it to the total electric field, the first thing I need is the total electric field. So I'm going to start up here with E equals vector 0, 0, 0. Every time I move the sphere, I'm going to calculate an electric field and add it to that. But if I don't have a value to start with, I can't add it to that. So that's definitely an issue. So there's my sphere. I have the position. I didn't have to draw that. I'm going to calculate DE now. So DE, no, I'm going to calculate R. R is the vector. It's the observation location, which is obs.pos. That's the vector location of that sphere. I can use that. Minus the vector location of the charge, which is just RQ. Now I can calculate DE. DE is K times DQ, which I didn't calculate. I'm going to put that up here. DQ equals Q. Oh, I can't do it right there. DQ. No, I can't do it right there either. I got to do it after N. DQ equals Q over N, right? If I break it into N pieces, that's how many, that's my electric field. DQ times norm R divided by mag R squared. In this case, I'm using the other version of electric field because I don't really care about writing out that unit vector. I'm just going to calculate it. Now I'm going to take that component and add it to my total. E equals E plus DE. And then I'm going to be done. And then at the end, let's go ahead and do this. Print E equals E newtons per coulomb. And let's put an arrow there too. So I need a scale. Let's call this E scale equals, it's going to be something like 1 times 10 to the negative fourth. I'm just going to pick. And let's put an arrow there. So E arrow equals arrow. Position equals obs.pos. It's at the observation location. Axis is going to be equal to E times E scale. And then let's put the color equals color dot cyan. I don't know why I picked that. This is cool. Let's see what happens. I should save this. Don't you think I should save this? I'm going to give you a link to the code. Okay, let's just, it doesn't like that. That's fine. Okay, there we are. Run it. Okay, that's way too big, right? There's my charge. Then my electric field's too big, but it did print out. So let's just make that, let's make that smaller. What if I make that 10 to the negative fifth times the scale? Because we're trying to draw an arrow in meters using an electric field in newtons per coulomb. That's pretty good. Let's make it a little bit smaller. Let's make it half as big. So 6, and make that 2. Okay, there we go. There's your electric field due to point charge. Now, let's check. Let's check our value with our analytical solution that we had before. So I'm going to calculate that and just compare, right? Because I don't know. But we can look down here. Is it in the x direction? It's not, right? It's not completely in the x direction. There's some y component there, but it's very, 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 very tiny, and that's fine because what's happening is I don't have the things completely centered because I shifted them all down a little bit, so it's not perfect, and that's fine. Now let's just calculate E theoretical. I'm going to do that down here. So ET is the theoretical value. And now I'm looking at my expression, which is K times Q divided by R. Let's call that, I did use R. Let's call this RT for temporary R. I can just call it X. X times the square root of X squared plus L over 2 squared. Now let's print that. Print ET equals ET in newtons per coulomb. Let's just compare those two. You compare those. I want you to compare those. You tell me how awesome this program is, because it is, right? Those are pretty much the same, and that's pretty awesome. Now you could also, if you want, we can move that very, very, very close to the rod and check if the approximate value is correct. I'm not going to do that. I'm going to do something else. I'm going to do something magical, right? Because we made the assumption in our calculus solution that we were on the x-axis. We assumed that the y components canceled. But what if they don't? Well, let's try this. What if I go over here? I have x. I can change that value. You can change that value and rerun the code. You can do that. My observation location is x, 0, 0. What if I put that at 0, x, 0? So it's not on the center line. It's over 0.06 and up 0.06. Well, let's run that. You'll see that now the electric field's pointing away, right? It's pointing away from the rod, not in the x direction. And we have a different value, and it doesn't agree with this because it's not the same thing, right? But now we've done a location that you couldn't really do with integration. This would be too difficult to integrate. Your integration would be just whacked out wackiness here. You wouldn't just have an x component. You'd have to deal with the y component. It'd be crazy. But with the numerical version, you can do it however many times you want. I can do things like change the value, the number of pieces. 50 is pretty good. You could do 500. You could do 5,000. It doesn't matter. But this is how we would do a numerical calculation. The idea of a numerical calculation is to break it into a finite number of pieces, not an infinite. With an integration, we break it into an infinite number of pieces. Okay, 33 minutes. If you made it through that, pretty good. Thumbs up. Link to this code down below. And I hope you enjoyed that. That was fun. I had fun. So really, that's the most important thing, that I have fun. That's it.